Obviously, we're going to bring you the latest news from the Phoenix probe on Mars. But first of all, something quite different. The biggest bangs of the universe, gamma-ray bursts. With me, Dr. Julian Osborne, and of course, Dr. Chris Lintop. Welcome, gentlemen. May I come first to you, Julian? Gamma-ray bursts, what exactly are they?
Well, as you say, they are the biggest bangs in the universe. They're the most extraordinary explosions. We think they're due to the deaths of generally massive stars, and we can see them probably across the entire universe.
But we can't see them with the naked eye, can we, Chris?
No, though they're very, very powerful explosions. Most of the energy is concentrated at the very energetic end of the electromagnetic spectrum. That's why they're called gamma-ray bursts. Gamma rays are even more energetic than X-rays. There's very little light in the optical that we can see, but there was a burst just a few weeks ago, in fact, Julian, that should have been seen with the naked eye. Yes,
magnitude 5.3, so if you were looking in the right direction at the right time and you had a dark sky, you might have seen it.
How long does it last?
Well, less than a minute, so you'd have to have been pretty lucky, frankly.
You will indeed.
But it was an extraordinary event. The previous most brightest gamma-ray burst in the optical was about magnitude 9, so this was very much brighter.
How far away is the most distant gamma-ray burst ever recorded?
Well, funnily enough, we detected the most distant one just a few weeks ago. It was at redshift 6.7, which means that the universe at that time was just 6% of its current age. And in fact, this is one of the very few most distant objects known in the universe.
How bright does it look?
This was not a very bright object, but of course, to instruments around Earth, it must have been intrinsically fantastically bright.
What kind of stars are liable to produce gamma-ray bursts? Can you elaborate on that a bit, Chris?
Sure, well, this is in some sense a fairly natural process, although it's violent. It's what happens to all massive stars, those much bigger than the Sun. What happens is they run out of fuel at the centre, there's nothing to support them, and so they implode. Most of the outer layers get thrown off in what we call a supernova. We see the emission from the radioactive material produced during that explosion, but the core collapses and produces either a black hole or something called a neutron star, a dense body, extremely dense, which we sometimes see as a pulsar if we have radio emission from the poles. And actually, these neutron stars have a role to play in some of the more unusual gamma-ray bursts.
Yes, in fact, there are two types of gamma-ray bursts, so-called long ones, which we think are associated with black hole formation as the massive star collapses. The long gamma-ray bursts may be a minute or so long. A short gamma-ray burst is one which is less than 2 seconds long and might even only be 10 milliseconds long. We have two neutron stars which were probably a binary star in the previous stage of their evolution. They're going round each other in orbit. That orbit shrinks and they spiral in, getting faster and faster, and eventually they hit each other and cause this most tremendous explosion.
Well, these things are not all that common, are they? But I believe 5 did occur on one special occasion a little while ago.
Yes, an extraordinary 24 hours. This was in the 19th of March of this year, 2008. Coincidentally, the day that the famous Arthur C. Clarke died, we had 5 gamma-ray bursts in one period of 24 hours, an extraordinary event for us, because ordinarily we are seeing just one every 3 or 4 days.
Knowing Arthur, he probably planned it.
Well, it was truly a remarkable thing.
They do leave traces, don't they?
Afterglow. We think it's the collision of the ejected material with the gas which was surrounding the star. The initial burst is coming from quite close to the star, but then later, as this material is rushing out at these hypervelocity speeds, it ploughs into the surrounding medium of the galaxy that the star is in.
Are there any nearby candidates? I mean, Eta Carinae, for example?
Eta Carinae is a reasonable candidate. It's not a binary, so we don't have that, but it is a massive star. It's more than 100 solar masses, and it's a weird-looking thing. I mean, you can see these enormous lobes coming off it, which is clearly some sort of extended envelope, and I'm sure there's mass loss going on. So I think this is a star that is losing its outer layers, its hydrogen and helium. So I think I can confidently predict that Eta Carinae might well produce a gamma-ray burst. The thing is, we'll have to wait a few billion years.
Another my first view of Eta Carinae through a telescope. It doesn't look like an ordinary star. It's a kind of red blob.
Yes.
And about 1840, It shone as the brightest star in the entire sky apart from Sirius.
In fact, some gamma ray bursts, well, at least one gamma ray burst is thought to have emitted a shell of gas a few years before it exploded.
So maybe that's what was going on in 80. We're now rampantly speculating. The hard thing is putting your finger on a star and saying, yes, definitely this one, but that's the best candidate.
But of course, space research comes in here. We have the SWIFT satellite.
Swift is amazing. You must talk about Swift.
Well,
this is your project.
So Swift is indeed pretty amazing, and it's amazing for two different reasons. One is it's focused on the subject of gamma ray bursts, and so it has a big gamma ray detector which looks at a large fraction of the sky waiting for gamma ray bursts. And when it detects one, it's able to react very quickly, and within a minute it will point its X-ray telescope and its optical telescope, which are co-aligned, onto this exploding star.
Is that why it's called SWIFT?
It is indeed why it's called Swift. The project has a kind of motto, catching gamma ray bursts on the fly, which is what Swifts do. They catch insects on the fly.
And the remarkable thing about this is it solves the big problem for gamma ray burst astronomers in that in the old days when these things were being studied more than a decade ago, all you'd know is that a gamma ray burst had gone off somewhere in a 2-degree patch of sky. Now, the full moon's half a degree across, so that's 4 full moons. And imagine saying somewhere in there is something that's caused this burst. It's hopeless. Whereas with Swift, because you go quickly to the X-ray and to the UV and the optical, you get down to it's this galaxy. And then you can trace it with big telescopes.
Yes, exactly.
And how do you measure their distances?
Through the redshift of the spectral lines. So essentially what we do is with Swift we measure the position of the burst, and that enables people on the larger ground-based telescopes to use their spectrographs to take spectrum, and then by identifying the emission lines in the spectrum they can say what the redshift is, and that's how you measure the distance.
Chris, what about Fermi?
Oh, well, this is the new American satellite, and it's doing something interesting. It's not specifically aimed at gamma ray bursts, but it's looking at a region of the spectrum we've never explored before. It's looking at a really high energy gamma rays, even way beyond what Swift, for example, is looking at, and they turn out to be important for understanding gamma ray bursts.
Well, they do. We hope that Swift and Fermi will simultaneously detect some gamma ray bursts, and it's very important to understand the total energy output of the gamma ray bursts, because that tells us how much mass is involved. And by looking in this very high energy part of the spectrum, we can measure the total energy output.
I want to ask Julia a question because I want to use gamma ray bursts, so I want to see if this is possible. What we love in astronomy is things that are what we call standard candles, things that are always the same brightness, or we can work out their brightness, because then when we see them in the distant universe, we can use them to measure the expansion of the universe. Now, gamma ray bursts would be perfect. They're bright, we can see them from 13 billion years ago. What hope do I have of getting an understanding of gamma ray bursts good enough that we'd know what brightness they are?
This is a fantastically controversial subject.
Yes, that's why I'm asking you. We've got an expert sitting here.
Yes. Well, so the question is, are they standardizable, really? You know, we use the supernova 1A in the near universe for measuring the expansion of the universe. And, of course, gamma ray bursts occur, you know, up to at least 6% of the age of the universe. They hold great promise. People are working very hard to understand the relationships between the energy they emit and their spectra, to try to work out if that relationship really stands up. There are plenty of people who think it does. There are plenty of people who think it doesn't.
Well, I wonder. Certainly we're going to learn a lot more in the foreseeable future. Julian, Chris, thank you very much. We can't usually see gamma ray bursts with the naked eye, and we certainly can see supernovae if they go off, but telescopically we can see what's left of supernovae, and one of these is the famous Crab Nebula. Out in the garden, Pete Lawrence is waiting for us to show us a supernova remnant, so out to Pete.
The Crab Nebula is a spectacular supernova remnant in the constellation of Taurus the Bull. If you look at a professional image of the crab, it looks absolutely amazing. Bright filaments and vivid colours. But what can you see if you only have an amateur average-sized telescope? Well, let's start by finding the crab. In fact, it's quite a simple thing to locate in the night sky. If you go out on a November evening and look towards the east or the southeast, say at around 9:30, you'll see the magnificent pattern of Orion the Hunter rising. If you can locate Orion, locate the 3 stars in the centre of the pattern, which form his famous belt, and extend them up and to the right, you come to a bright, slightly orange-hued star, which is known as Aldebaran, the brightest star in Taurus the Bull. Next to Aldebaran is a V-shaped cluster of stars, which is known as the Hyades. Now, if you extend the arms of the Hyades across to the left, you eventually come to 2 third-magnitude stars, which mark the tips of the bull's horns. And it's the bottom or southern tip, which is marked by the star Zeta Tauri, which is the key to locating the Crab Nebula. If you look at this area by centering Zeta Tauri in a pair of binoculars or through the finder scope on your telescope, you'll see that there is a pattern of stars. Zeta Tauri, fairly bright at the bottom, and then 3 other fainter ones. They form, if you like, a squashed kite shaped in the sky. And the key to finding the crab is to use the one on the left, join it to the one at the top, and then extend the line again for about half the distance again. If you do this, you'll be pointing exactly at where the Crab Nebula is in the sky. Well, through binoculars, it is possible to see it, but it is quite difficult, and you need very clear dark skies to succeed. And it looks like a faint dot, faint fuzzy extended dot. A small telescope will improve the view, and you can see it as a slightly extended patch of light. Say a 4-inch or a 6-inch telescope will reveal that the patch of light isn't evenly illuminated, it's slightly mottled. If you want to see the incredible detail which is in the nebula, you have to go to a much larger telescope, say a 16-inch. So what is the Crab Nebula, and where has it come from? Well, the Crab Nebula is a supernova, or is the remnant of a supernova explosion, which was observed about 1,000 years ago. The Chinese and Arabian astronomers of the day observed a new star in the night sky. In fact, this was no ordinary star. It was incredibly bright compared to the average stars that they could see. It was estimated to be about magnitude -6, which makes it 4 times brighter than Venus. In fact, it was so bright that it could be viewed during the day, and it was observed for 23 days consecutively in broad daylight. In 1844, the Earl of Rosse, using his huge 72-inch reflecting telescope known as the Leviathan of Parsonstown, observed it and sketched it. And his sketch resembled a crab, and that's where it got its nickname from, the Crab Nebula, the name we know it by today.
Pete, thank you very much. And now, back to Phoenix on the surface of Mars. Chris Seminova in Arizona to bring us the latest news.
If I want to find out how this magnificent desert landscape formed, I can study the rocks that make up the mountains. I can pick up soil and look at how it behaves. If I want to do the same for the vast northern plains of Mars, I have to go there. And that's what the Phoenix spacecraft has done. Phoenix is NASA's latest mission to Mars. It landed last May in the Martian Arctic Circle. Its mission is to scratch and then sniff the surface of Mars, looking at the soil under the microscope and testing its chemistry and its composition. It does this by digging into the soil, carefully choosing samples for its suite of miniature laboratory instruments. Phoenix Mission Control is here in Tucson. The Sky at Night last visited in June, when Phoenix had been on Mars for a month. The whole place was buzzing with scientists dashing to get a hold of the latest results and the latest images, and then arguing over them.
Oh, that's a steep back wall, isn't it?
Oh yeah.
And that really did go. That really did dig in at the front there.
100 days have passed on Mars since I was last here, and things have changed somewhat. What was a bustling control center has become an oasis of calm. But meanwhile, on the red planet, Phoenix still has work to do. Mars has become a harsher place since then, too. The long days of an Arctic summer are gone, and now Phoenix has to endure the onset of the Martian winter.
Enemy sequence initiated.
Peter Smith has led the mission since its conception 6 years ago, and it's been quite a journey. Well, how's Phoenix?
Phoenix is doing well, and I'm a little bit surprised it's beyond its warranty. Its warranty was 3 months. We didn't expect it to die after 3 months, but it's gone on, and the spacecraft shows no sign of any aging. So we think it's there all the way to the end when winter sets in.
Let's start with talking about the weather, seeing as you mentioned it. We've seen clouds in the sky now, even snow we hear.
Well, it's getting a little blustery, you know. It's fall weather. There's frost on the pumpkin, so to speak, and it's known from orbital missions that polar weather is a lot more exciting than equatorial weather. And you can see cyclonic wind patterns developing and whipping across the northern plains. We've actually seen low pressure cells move by. And the winds increase, the winds twisting around as weather patterns come past us. And then just recently, we've seen streamers under the clouds with our laser experiment, and this is indicative of snow. Now, the snow doesn't always get down to the surface, and remember, Mars' atmosphere is very thin, so the snow tends to sublimate before it reaches the ground, or may come down as just little sparkling dust, what we call diamond dust. And we're starting to observe that sort of effect. That means we're headed towards the cold season, the winter season of the polar plains of Mars.
You mentioned Phoenix is now entering winter. How bad is it going to get?
Well, the temperature's been dropping. During the summer, the high temperature in the warmest part of day was maybe minus 20 degrees centigrade. Now it's down minus 30, minus 35, and the nights are getting very cold. It could be minus 100, 110. And it's headed down to minus 130. That'll be the temperature throughout the entire day in the winter, minus 130.
We have this wonderful view of the landing site. What have you seen, and what did you expect?
Well, it's similar to what we expected from the pictures from orbit. It's a landscape that's modeled by the expansion and contraction of ice. And this happens through the seasons, and the ice tends to buckle under those pressures. And so we see a surface that ripples out towards the horizon. And these are called polygonal or patterned ground features. And we are fortunate enough, and this is where we didn't expect this to happen, is that we can actually reach to the center and to the troughs between these mounded features on the terrain. So we look at two different types of landform, and we're digging right now down to the surface, and we're going to expose ice across one of these hillocks and through the trough, and that'll tell us a lot about how ice forms in these plains.
We keep talking about ice. Can we be absolutely sure it's water ice?
We are positive. We have actually scraped up some chunks and put it into our TIGA instrument, which has a mass spectrometer, so we can boil off the water from the ice and actually measure the mass of the individual particles. And of course, it's oxygen plus 2 hydrogens, mass of 18. We see it directly.
Some 4 billion years ago, Mars was a planet covered in water. And it's the presence of that water, albeit locked up in ice beneath the surface, that drew the Phoenix team to this part of Mars. Previous missions, like the rovers Spirit and Opportunity, have found evidence of minerals that can only have formed in the presence of liquid water. Their results suggested that the ancient seas of Mars were acidic, and so Phoenix's team were expecting more of the same from their part of Mars. Instead of acids, though, they found alkaline soil.
We have, of course, read the papers from the rover missions, and they were very adamant that what we might expect to find on Mars, a typical Mars surface, would be sulfate rich. And so we designed some of our instruments to handle even large amounts of sulfates. And we have not been able to prove the existence of any sulfates so far. And it turns out that the story of the alkalinity, the pH being around 8, 8.5, somewhere in that range, is governed by the calcium carbonate that we've discovered in the soil. This is on the Earth we call it limestone, or sometimes chalk. I mean, after all, the cliffs of Dover are chalk. That's calcium carbonate. And that's what we're seeing. So if you remember your chemistry, carbonate is a buffer. In other words, if you try and change the pH away from 8 to 8.5, it resists it. That's why you take antacids and you use calcium carbonate. It reduces the acidity. And so if the soil tries to push itself away from alkaline type of soil, the calcium carbonate brings it back.
The Phoenix landing site bears the scars of recent history. There's a nearby fresh-looking meteorite crater and even a volcano.
My suspicion is, and that's what it is at the moment, is that we are still on the flanks of a volcano, and the flanks are formed by the ash falling down from the volcano. And so the soils are not ancient soils, because this is the most recent part of the volcano, is the distant flank. So this is not a 3,000 or 4,000 million year old surface. It's fairly recent. So when we see that the soils are modified by water and have formed calcium carbonate and perhaps clay or phyllosilicate, another word for various types of clay, then it's most likely it happened recently. It could have been caused by the impact into this terrain right next to us.
If you've got ice and you slam a meteor into it.
You slam a meteor into it, it's like a nuclear weapon has been exploded. So you're going to send steam shooting out into the atmosphere from the ice under the surface. It's going to interact with the CO2, the carbon dioxide atmosphere. You could form carbonate in that process. But still, that's recent. This isn't the ancient materials that the rovers are seeing.
The heart of Mission Control is home to a life-sized, working replica of Phoenix. It's here that the team come to experiment, rather than taking risks with the real thing. We've arrived at a dramatic moment. This is where the team simulate what's happening on Mars, and right now the entrance to one of the instruments has been blocked by a pile of soil left over from a previous delivery attempt. The team are trying to work out how to use the robotic arm to scrape off that soil, a simple enough task on Earth, but much harder when your spacecraft is 200 million miles away. Rick and his team are working with scientists based in California at the Jet Propulsion Laboratory. They're watching the latest maneuvers of the robotic arm as it tries to shift the soil that's sitting on top of the chemistry instrument.
What we're trying to do here with the EM is to simulate or model what we have on the planet, which is a big pile sitting on top of the wet chemistry cell number 3, and they're using the robotic arm to try to push the dirt through the funnel and down into the cell. So we're practicing that here, and as you've seen, it takes us a long time. We move it a little step at a time, but we're trying to get the sequence down such that the robotic arm team can build that sequence, and then when it goes to the spacecraft, it'll be much quicker and just, execute it.
Of all the scientists involved in Phoenix, Bill Boynton's had the toughest time. His TIGA team have had huge problems just getting the sticky Martian soil into their instruments' tiny ovens.
This really was a surprise. We were actually anticipating there would be ice present. We actually knew that from earlier results with the gamma ray spectrometer on Mars Odyssey. But the fact that when the ice warmed up a little bit, that perhaps the salts in it would make it get a little bit soft and sticky was not something we really had anticipated.
Well, we know salt changes melting point. That's why you put salt on the roads in the winter.
That's right. And we have an instrument here, the WICL, or Wet Chemistry Lab, is designed for measuring salts, but it turned out we just had so much more salt than we expected, and these salts called the perchlorates happen to be very effective at lowering the melting points, and so I think that really caught us by surprise.
Time's running out, the nights are getting longer. What will TIGA be doing in its last month or so?
Well, we've still got a few more ovens left to fill, and one of the things that's still on our plate is to figure out what samples are going to go in there. We'd like to make one more try at a ice-rich sample. We haven't yet been successful in getting a lot of ice into the oven. We got a small amount of ice way back, but we still want to try again for a sample which has an awful lot of ice. We'll probably want to get another sample from beneath the surface, but not really part of the ice.
Phoenix has 1 or 2 other items left on its shopping list.
I think of our progress so far as we're about 90% of the way there, and that last 10% would be so wonderful. But if we don't get it, that's still a great mission. What we have left is to try and make a case for organic materials in the soils of Mars. This is a wonderful result if we can make that case. So far we see carbon dioxide released in our TIGA measurements, but we don't know if that's a carbonate or some other mineral, or is it terrestrial organic contamination, or don't know what it is. So the only way you can figure that out is to have a blank. That is something that has the terrestrial organic materials and shows you what the signature is.
Something that came from Earth with
something
the
that came
spacecraft.
from Earth. It could be an empty oven that's just carrying what it carried from Earth, or it could be what we have, an organic-free blank that we tried to put into a cell just recently. It's very fine white material. We poured it in, the wind gust kicked up, it blew it all away. Oh, so frustrating, we're that close.
You must just want to go up there and pick it up yourself sometimes, these
Hey,
tasks.
we're 200 million miles away. It's hard to get a hand-on experience.
I didn't say you should do.
It's frustrating, and often you make silly mistakes just by being so far away and only being able to see through eyes of cameras and encoders on robotic arms and that sort of thing.
What lessons can we draw from Phoenix for future landers on Mars?
Well, as you might guess, the people who are doing the sample collection and preparation for the Mars Science Laboratory, which is the next mission that's getting ready to go to Mars, it'll be there in 2 years, they're worried about the properties of the soil. I mean, if it's just as sticky and clumpy and has the bad behavior of the soil we've seen, they would like to know about it now while they can still change things. So they're trying some very sticky soils in their experiments.
Mars is now moving behind the Sun as seen from Earth. Conjunction is in mid-November and you'll lose all contact with the Phoenix spacecraft. Will that be the end for the mission?
Well, we make predictions, and that's all we can do based on our models of the atmosphere and our understanding of the hardware. We predict we're still able to do a lot of the experiments to finish up our science through October. And then November, we'll be having to turn off heaters in order to get through the day. As you turn off heaters, things start to break. So throughout November, we'll continue with pictures and weather reports. And then finally, towards the end of November, it'll just be the simplest things, occasional picture, pressure and temperature, and that's about it. And that'll be how we continue until the end, which is probably somewhere mid-December.
Having first visited the Phoenix team 2 years ago before the launch, it's been wonderful to follow their mission ever since. As winter sets in, we can now only watch and wait as Phoenix loses power. Eventually, it will end up trapped within the Martian ice cap. That will be the end of Phoenix, but it leaves behind an invaluable glimpse of life on the eerie Arctic plains of Mars.
Chris, thank you very much. Well, when I come back next month, we're going to look at planets of other stars. Until then, good night.